So, we will assume that lambda 1, lambda 2 dot 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 lambda m are distinct. Okay. This is a special case, not always the case that this is true, okay, but this is the most intuitive case. Okay. And also we normalize nu I and pi I such that pi I nu I is equal to 1 for all I. Okay. These eigenvectors can be scaled such that pi I nu I is equal to 1 for all I. For the special case I equal to 1, which this is already true, right. This is just saying that for I equal to 1, this is pi E equal to 1, right, which means that the sum of all the stationary probabilities is equal to 1, which we already know is correct, right. But we are going to do this for all the eigenvectors. Okay. Now, here is an interesting lemma. Say for I not equal to j and distinct eigenvalues lambda 1 to lambda m, we have pi j nu I is equal to 0. Okay. So, if you take the dot product between these left eigenvectors and right eigenvectors for unequal indices, you get 0. Okay. The way you prove this is you consider pi j p nu I, all right. So, one way to write this is to realize that p nu I is just lambda I nu I, right. So, I can write this as lambda I pi j nu I, and the other way to write this is to take the left eigenvalue equation and write this as lambda j pi j nu I. Okay. And these lambda j and lambda I are not equal, right. You are assuming distinct eigenvalues. This is the special case of distinct eigenvalues. This implies that this implies what you want, place pi j nu I is equal to 0 for I not equal to j, all right. So, this will be useful in writing out the diagonalized form of the matrix P. Diagonalized. Since the matrix P is assumed to have distinct eigenvalues, you can always write a diagonal representation of P or diagonal decomposition. Namely, P can be written as U lambda U inverse, all right, where lambda. So, I should tell you what these matrices U and lambda are. This lambda is simply the diagonal matrix of all the eigenvalues, all right. U is the matrix of all the right eigenvectors made into a matrix, all right. You can always show that this sort of diagonalization can be done as long as the lambdas are distinct, right. Now, what is U inverse? Okay. So, what you can show using the above lemma is that U inverse, which is in this equation, will simply turn out to be the matrix in which all the left eigenvectors are arranged in their rows. Okay. This follows from the fact that, so you can easily verify that u inverse, what I claim to be u inverse is in fact the inverse of u by simply noting that the pi's and pi I lambda I is equal to 1 for all I, and pi I lambda j, I think I made a mistake, I beg your pardon. So, these are the eigenvectors. So, I should be writing news, right, I made a mistake. So, you know that pi I nu I is equal to 1 and pi I nu j is equal to 0, right. From that you can prove that the structure of u inverse is like this, right. This is using the lemma above. Okay. So, this is great. So, this kind of a diagonalized representation is possible. Okay. If you write out this matrix P, another way of writing P equal to u lambda u inverse is simply to write sum I equals 1 to m lambda I nu I pi I. Okay. So, nu I pi I is a rank 1 matrix. Okay. This is nothing but the spectral decomposition of the matrix P, or it is just a rewrite, you can just look at it as a rewriting of the equation P equal to u lambda u inverse. Okay. Next, how about P power n, right? Can you write a similar spectral decomposition of P power n, all right. Interestingly, the matrix P power n has eigenvalues lambda I power n, right, where lambda I are the eigenvalues of P, okay. But the eigenvectors will be the same, okay. You can show that P power n nu I will be lambda I power n nu I, and similarly for the left eigenvectors, okay. So, all in all you can write the matrix P power n will have a diagonal representation u lambda power n u inverse, okay. So, only the diagonal matrix gets raised to the nth power, right. This is basic linear algebra or you can write it as P power n is equal to sum over I equals 1 to m lambda I nu I pi I, lambda I power n nu I pi I, right. This is the spectral decomposition of the matrix P power n, okay. But we know that lambda 1 is equal to 1, we have taken lambda 1 is equal to 1 and nu 1 is equal to E and pi 1 is equal to the stationary distribution pi. So, I can just write that out, I can just pull that out as a special term. So, I will have E pi plus sum over I is equal to 2 to m lambda I power n nu I pi I, okay. So, this is an important equation, this is nothing but the spectral decomposition of P power n, all right. So, P power n, so this is true for all n greater than or equal to 1. So, for all n greater than or equal to 1 we have an explicit expression for P power n which is the matrix of all pi pi pi, right, plus a bunch of terms, right. Now, the question is what happens to these terms I is equal to 1 to m of I is equal to 1 to m lambda I to the n nu I pi I, right. So, if this sum from I equal to 2 to m goes to 0, then we can easily conclude that P to the n converges to E pi, all right. Now, what happens is the following, see these eigenvectors which are the eigenvector, see these eigenvalues lambda I, which are the eigenvalues other than the one eigenvalue, these can be shown lemma, these can be shown that to be having magnitude less than or equal to 1. Okay. Actually lambda 1 is equal to 1, right, and the others have magnitude less than or equal to 1. Okay. The way to prove this is the following. See, remember that the lemma only says that the absolute value is less than or equal to 1 for I is equal to 1 to m. I can just write I is equal to 2 to m because I know that lambda 1 is equal to 1. So, maybe I should just write I is equal to 2 to m, alright. Now, if all these lambda i's from 2 to m have a magnitude strictly less than 1, then I will have convergence of p to the n to e pi. We know that in the case of an ergodic Markov chain, this convergence happens. We already proved it in Perron's theorem. So, for a ergodic Markov chain, we can conclude that the absolute value of lambda i's is actually less than 1, alright. In general, if you do not have ergodicity, the eigenvalues are less than or equal to 1. Okay. The way you prove this lemma is as follows. You consider the left eigenvalue equation, lambda I p power n is equal to, sorry, lambda I pi I is equal to lambda I power n p pi I is equal to pi I p power n, alright. You consider the jth component of this. This is just the left eigenvalue equation. Left eigenvalue equation for pi I. So, if you consider the jth component of this, you will get lambda I power n pi I jth component is equal to sum over L pi L p I j p L j n. So, it will be pi I L p L j n. Okay, so, the way you prove this lemma, is to write out the left eigenvalue equation lambda I power n pi I is equal to pi I p to the n, right. This is just the left eigenvalue equation for p power n. Now, you look at the jth component of this equation, you get lambda I to the n pi I j, which pi I j is the jth component of the row vector pi I, is equal to sum over L pi I L p L j n, alright. This is true for all j equals 1 to m, right. From this we can get lambda I to the n is equal to, so maybe I should put absolute value. I can write is less than or equal to absolute value of lambda I to the n pi I j is less than or equal to sum over L absolute value of pi I L, right, and the absolute value of p L j n is less than or equal to 1, right. So, I can upper bound that by 1, alright. So, this just turns out to be sum over L absolute value pi I L, okay. This is true for all j equals 1 to m. Now, you choose j, this is true for all j, the above equation. So, choose j such that j is equal to argmax absolute pi I k, okay, over all these. So, you to take the j for which that guy is, this absolute value is the biggest, alright. Then what happens is that you will get absolute value of lambda I to the n is less than or equal to sum over L absolute value of pi I L over absolute value of pi I j, okay. And you have chosen j such that these ratios are all less than or equal to 1, because you have chosen the j for which absolute value of pi I j is the largest, right. So, each of these terms in the sum ends is equal to is less than or equal to 1, which means that the sum is less than or equal to m, right, and this is true for all n greater than or equal to 1, right. And the only way that absolute value of lambda I to the n is less than or equal to m for all n is if absolute value of lambda I is less than or equal to 1, right, because if the absolute value of lambda I were bigger than 1, then some nth power will be bigger than m, right. So, and that is not possible, right. So, we have shown that all the eigenvalues are less than or equal to 1. The first eigenvalue is of course equal to 1, and then the subsequent eigenvalues are all less than or equal to 1. Now, we know that for an ergodic Markov chain, we know that p power n converges to e pi as n tends to infinity, right. How do we know this? This we know from Frobenius theorem, which means that if you look at this spectral decomposition, which means that the sum from 2 equal I equal to 2 to m must go to 0, right, and that means that all these lambda i's for 2 to m must be have absolute value strictly less than 1, all right. So, this implies absolute value of lambda I are strictly less than 1 for I is equal to 2, 3 dot 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 m for an ergodic DTMC. All right. So, you have this kind of a convergence. So, p to the n, I am just rewriting this equation, p to the n is e pi plus sum over I equals 2 to m lambda I to the n nu I pi I, and all these are these eigenvalues will be all these eigenvalues are have absolute value strictly less than 1, and therefore, all these terms go down exponentially fast, right, geometrically fast, and therefore, we have a very clear understanding now that p to the n converges to e pi geometrically fast, and we even have the rate of convergence, right. The rate of convergence for an ergodic Markov chain is governed by the second largest eigenvalue of p, i.e., you look at the I star for which has the largest magnitude of this lambda j, where j is from 2 to m, okay. Remember lambda 1 is equal to 1, you forget that and you look at all the other eigenvalues and take the eigenvalue with the largest magnitude, okay. Overall this is the eigenvalue with the second largest magnitude, the first one, the largest eigenvalue being 1, and there is a whole bunch of eigenvalues with absolute value strictly less than 1 for a ergodic Markov chain, and you look at that index for which the absolute value of the eigenvalue is the largest, all right. Then lambda I star, absolute value of lambda I star will determine the rate of convergence, okay. rate of convergence. Right, and this eigenvalue which has the second largest magnitude is sometimes known as the Perron Frobenious eigenvalue. So, what is the Perron Frobenious eigenvalue of P? There is a eigenvalue which is equal to 1, you forget that, and look for all other eigenvalues, the other m minus 1 eigenvalues, you take the one with the largest absolute magnitude. Okay. Of course, the lambda I star itself may be complex, but you are looking at the eigenvalue with the second largest absolute value, and that is known as the Perron Frobenious eigenvalue. And this Perron Frobenious eigenvalue determines how fast the matrix P power n converges to E pi. All right. If the Perron Frobenious eigenvalue is has a magnitude very close to 1, then the convergence is very slow, and conversely, if the absolute lambda I star, this Perron Frobenious eigenvalue, if it's fairly small in magnitude, then the convergence to steady state pi is very fast. I will, so this is a good exercise. It basically just uses linear algebra in the sense of the spectral decompositions, and we get a very fine grained understanding of how this P power n behaves. All right. So, for ergodic Markov chains, we have a very precise characterization of the rate of convergence. We know that it is geometric already from Frobenius theorem, but the exponent in the geometric convergence is exactly characterized to be the second smallest second largest eigenvalue in magnitude, right. If the Markov chain is not ergodic, there could be other eigenvalues lambda I with absolute value equal to 1, all right. So, in that case, P power n will not converge to E pi, all right. So, I will briefly discuss what happens in those cases. So, in the ergodic case, in the aperiodic case, you have convergence to E pi, which is geometrically fast. In the periodic case, what happens is you will have other eigenvalues whose magnitude is equal to 1. Okay, you will have eigenvalues on the unit circle. Okay, so these I will just state without proof. For a periodic DTMC, let us say I have one recurrent class and that recurrent class is periodic. In this case, we will have d eigenvalues on the unit circle in the complex plane that are equally spaced. Okay, this I am not going to prove. What I am saying is that if you have this, let us say this is the unit circle on the complex plane, I know that there is an eigenvalue at 1 always for a stochastic matrix. You will have other eigenvalues which are equispaced on the unit circle. Okay, you will have d such eigenvalues, and the spacing between all these guys will be equal, and this angle will be 2 pi over d. Okay, so, we will have d equally spaced eigenvalues on the unit circle for a period d Markov chain. All right. So, some of these, not all these, so you will not have convergence. If you this expression out here, this spectral expansion here, right, this spectral expansion is still valid, except that these lambda I power n's, some of these lambda i's have magnitude equal to 1, they lie on the unit circle. So, the nth power does not converge to 0, okay, that is what happens in a periodic Markov chain. The way you prove this is using the fact that in a period d Markov chain, you can partition the states into a d separate subsets, where all the transitions go from S0 to S1, S1 to S2, and so on till SD minus 1 to S0. We saw this result already, and using that result we can argue that the matrix P will have to have a certain rotating structure among these blocks going from S0 to S1 and so on, and then we can prove that these eigenvalues lie on this unit circle equally spaced. All right. There is a guided exercise in Gallagher book for this, but I am not going to prove it here. Okay. The other case I want to point out is that if you have C recurrent classes, if we have C recurrent classes, what will happen is that we will have the multiplicity of the eigenvalue 1 will be equal to C. Remember that in the previous discussion I have only covered the case when all the lambda i's are distinct, all right. That is not the most general case. If these lambda i's were not distinct, then you will have a bit of an issue in the sense that the eigenvectors lambda i's, so the eigenvectors nu i's and the left eigenvectors pi i's may not span the space, span Rm, all right. In that case, this sort of a diagonalization u lambda u inverse may not work. Okay. So, if you have repeated eigenvalues, you may not be able to appeal to the mechanism that I have talked about using diagonalization. You have to go into a formalism called Jordan form in linear algebra, which is in my opinion not very directly intuitive for the study of Markov chains. I am just saying that you can do it using Jordan forms. I am not getting to that in detail. In the specific case when you have C recurrent classes, then the multiplicity of the eigenvalue 1 will be C. Okay. So, there will be C repeated eigenvalues at lambda equal to 1, okay. And you will have C linearly independent left eigenvalues, left eigenvectors that solve pi p equals pi. Okay. So, there will not be a unique pi like this. Okay. There will be C linearly independent solutions to pi p equals pi, and of course, all the linear combinations of these linearly independent solutions will also be solutions, all right. So, if there are C recurrent classes, you will have C repeated eigenvalues at lambda equal to 1, and correspondingly you will have C linearly independent solutions to pi p equals pi. Okay. So, these two things I am not going to prove. Okay. So, this is where I will stop.